So, welcome everyone to the AI Research Bites. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research team. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from Shubham Gupta on our latest advancement on efficient and interpretable retrieval representation. It will be followed by a 10-minute Q&A. Shubham is a PhD student at Mila, working under the supervision of Professor Pascal Germain and Sem Subakam at Université Laval. He earned his master's degree at University of Waterloo, and his research focuses on explainable modeling and adaptation across domains such as text, audio, and vision. Up to you, Shubham.
Thanks, Fanny. Today, we are going to talk about ReTreever, which is a tree-based document organization for retrieval systems. It's a joint work with a bunch of amazing researchers, Ji Chao, Tianye, Sems, Siva, Peruz, and Valentina. Our talk will include some forward-looking statements and will also detail some aspects of our research. So what's the agenda for today? Today, we are going to introduce what retrieval systems are and how they exist in the world of LLMs today. We'll introduce our work, ReTreever, and we'll talk about as to why you should care about ReTreever. So what is a retrieval system? A retrieval system is something that quickly finds and returns documents to answer any questions correctly. So let's say there is a person who has some question. A friendly retrieval system will go in, go through a bunch of documents, and will retrieve just those right documents that contain the answer to your question. Why do we even need a retrieval system? Aren't LLMs good at just answering everything today? And so here we have a small case study kind of to portray as to why LLMs are not enough to answer all questions accurately. Let's say there is a new product in the market, Classes++, and you want to ask an LLM about what these Classes++ are. And what you have in mind is classes, which are these VR glasses, which overlays a lot of information onto the real world. But LLM isn't aware of these classes. They are a new product. And therefore, it takes its best guess and says that, oh, it's these super cool glasses that corrects every vision. But that's clearly the false information. So what's happening here? If we have a retrieval system in the pipeline, and as the user asks about Classes++, the retrieval system can fetch some details about these classes, can fetch some specs, and the LLM can now answer this question much more accurately. It will say it is these cool VR glasses that overlays digital data into a real world view. And not only that, it can also include citations and links to the specific documents that the retrieval system retrieved to bring in confidence for the user to go and check those resources themselves. So it's really much easier to come up with the right answer when you can look at just a few very important relevant documents instead of relying on the world knowledge of an LLM. You can also answer questions accurately with this process, even if the LLM was not aware of the answer to begin with. In this case, for example, it was not aware of Classes++. And also, you can provide these citations. The user can go in and verify the accuracy of the provided answer because of these written documents and the citations that go along with it. So why retrieval systems? It helps us to ground on private and custom data. It reduces hallucinations in LLMs. It increases their accuracy. It also incorporates an efficiency element to it. You can have millions of documents in your private database, and a good retrieval system can fetch just those handful of correct documents that correspond to a particular query that makes the job of a downstream model easier. It also introduces a lot of flexibility in the system because now you can change the underlying database without having to do an expensive LLM fine-tuning. You can add documents, you can remove documents, and you can completely overhaul your database altogether without touching any other part of this pipeline. It also introduces some inspectability. Now you can look at these specific documents and you can ask these questions as to why these documents were considered for my query, why specifically these documents were used, and these will also help explain the answers given by an LLM downstream. So I want to stress that this inspectability is very important. Let's say you have a system in production where a user asked a question and the user did not get a very good answer. And so they are asking as to why did I get a bad answer to my question? And because of these interpretable retrieval systems, we can ask questions like these, that maybe that particular question could not be answered. Maybe the LLM was not given the right sources to look at. Maybe the LLM didn't understand the sources we gave to it. And we can also ask as to why certain specific documents were returned for this specific question. And all of these questions can be answered much more nicely if we have an interpretable retrieval system. This inspectability in today's AI world is a very important aspect. I'll give a brief retrieval primer. The very basic way of doing retrieval, the first generation is around sparse encoders. In the sparse encoder world, when we have a question and we have some documents, we match the documents to these questions based on keyword matching. So we say that your question is asking about classes plus plus. The retrieval system will go in and look at the documents that contain the word classes, contain some of the relevant words to your query, and will return documents based on that. And now its strength is that it is very fast. It is very interpretable also. Because now when you go about asking the question, why particular documents were returned for your query, you have the answer in front of you. You say, because you were asking for classes plus plus, and these documents contain the word classes, that's why these documents were returned for your query. But it also has weaknesses. Like it only works if the exact term matches. It does not understand the semantics at all. Like it does not work if you use some synonyms. If you change the language a little bit, these kind of methodology fails. And it does not understand the underlying meaning of the sentences in a document. It is looking at the exact words used in the documents, which limits its applicability and also limits its accuracy. The next generation of encoders is dense encoders, which use these complicated transformer models mostly that take some text and convert it into an embedding, a representation in some continuous vector space of, say, 1,000 dimensions or 500 dimensions. And these embeddings are very knowledgeable. They're very succinct. They're very smart. Their strengths are to grasp the meanings. They are robust and they are accurate. This does not suffer from the semantic understanding part that we talked about in sparse encoders, because there's a lot of studies done on these kind of embeddings, which show that they learn relationships like man and woman and king and queen and stuff like that. But they are very succinct and nice representations. But their weaknesses are that to train them, it requires a lot of data. It requires a lot of compute, and they lack interpretability completely. So now a document is represented as this 1,000-dimensional vector in an embedding space, and it is very opaque. If you were to ask as to why was this document assigned this particular vector, we won't have a very clear answer to give as to why that is the case. To circumvent this issue, there is a class of retrieval systems which are hierarchical retrieval systems. What they try to do is they organize documents into these multi-level structures, which go from some coarse representation to some fine representations. Their strength is that they improve interpretability. The idea of assigning these documents from coarse to fine representation is the interpretable portion, saying that you can track the flow through this system and say that what is the coarsest classification of this query, and then you can go deeper and deeper into much more finer details to understand why particular documents were returned for a particular query. By nature of this hierarchical structure, their weaknesses are that they are expensive to train. A lot of these hierarchical structures rely a lot on LLMs. There are a lot of LLM queries that have to be done both during their training procedure and during their inference procedure. And these LLM calls are very expensive. Using an LLM inherently in these training and inference makes these systems very hard to train, and their cost of inference is also very high. In this realm lies our work, Retriever. It is a hybrid approach to the hierarchical systems and dense encoders. It introduces a hierarchical organization, which looks like a complete binary tree. It is interpretable. It has fast inference. It is also accurate. And it also goes to these coarse-to-fine representations. And I'll touch upon these one by one. So let me first explain a little bit as to how a retriever works. In a retriever, every node in the tree learns a routing function. The responsibility of this routing function is simple. It looks at the document that is supposed to be routed through this tree, and it gives me a number that is a probability of whether this document should be routed in the left subtree of this node or the right subtree of the node. As a result of the routing function that we learn at each node of this tree, we can combine all these probabilities given to these edges into a probability distribution of how this document is assigned to the leaves of the tree. So as a result of this whole routing learning methodology, we get an assignment of a document to the leaves of the tree, and it's a probabilistic, soft probabilistic assignment. And these assignments now serve as the dense representation of the text. How do we train such a model? We train it via a contrastive loss, and it's trained specifically in our case, in our work for question answering tasks. So what does it mean that it is trained via a contrastive loss? Let's say a particular user has a particular query, which is the first row here, and then there is a document that contains that answer to that query. That's the second row here. But there are also these other documents which are colored in red, which do not contain the answer to this query. So we train these routing functions in these trees in such a way such that it encourages the dense representations that we get for the user query and the positive document to be close to each other. So if you see that these two colors, they kind of match with each other, like they're very peaky towards this node while they tail off at the other ends of the representation. But it also encourages that the documents that do not contain the answer to this query should have a distribution which is different from the distribution of this query. By encouraging these kind of closeness between user query and the positive documents and distance between the user query and the negative document, we're able to train our tree in a robust and accurate fashion. A retriever is interpretable. As I touched upon this earlier, a hierarchical systems bring in inherently an idea of interpretability. And if you notice from our last slide, we are not training specifically to learn thematic groupings of documents, but by the nature of the hierarchy introduced there and by the nature of the training, these thematic document groupings emerge on their own. For example, we noticed that this node 5 in our tree had very high probability assigned to all the documents related to media, like both TV and publishing side. And as we drilled down, we went further down the tree, we saw that its subtree at node 11 was very highly focused on publishing, and the subtree at node 12 was very highly focused on TV. And as we go down the tree, we see that it becomes finer and finer collection of documents being assigned large probabilities to those nodes. So this is what interpretability here means, that we can follow the tree path to debug as to why certain documents were fetched for a particular query, and it gives us an understanding in these thematic groupings as to what kind of groupings did the model assign to a query and to the documents. Retriever is much faster than other hierarchical methods. Here we compare Retriever to other state-of-the-art hierarchical methods right now, hierarchical k-means, hierarchical GMM, and Raptor. And we notice that Retriever is really fast to do inference. What we are measuring here is milliseconds per query. So we're measuring how many milliseconds it takes to answer a query on a trained model. And for Retriever, it's close to around 20, while for other methods, it ranges from around 200 to close to 1500 in this case. We also have this advantage of not having to train Retriever every single time our database is updated. Well, that is required for some of these other methods. Here we have produced results for two data sets. One is NQ and one is replica. These are both question answering data sets, and they are widely used in industry and in academia to measure the efficacy of retrieval systems. Retriever also maintains accuracy. Here, what we are measuring is this metric called as recall at 10, which is a measure if a system can show at least one relevant item within the top 10 results provided by the retrieval system. So we recall at 10 would be high if among the top 10 documents provided for a particular query lives the right document that contains the answer to this query. Here we compare Retriever with BGE, which is a well-accepted encoder, dense encoder to encode text into these dense embeddings. So we are comparing as to how does Retriever perform in comparison to BGE over 4 different data sets. And we see that Retriever either matches or outperforms BGE encoder on these various QA data sets, while remember that Retriever is interpretable while BGE encoding is not interpretable. Retriever also gives coarse-to-fine representations. What I mean by that here is that a retriever tree has a very similar structure at every single level of the tree. So we spoke earlier as to how when we looked at the probabilities, we get a probability distribution at the leaves of the tree. But if we look at the layer above the leaves of the tree, if we are looking at this level, then we also see that this is also very similar to the leaves. There is no structural difference between different levels of the tree. So if we are fetching the probability distribution as a dense embedding from the leaves, we can also fetch it from other levels. So in this case, from the leaves, we get a representation of size 8. But if we were fetching it from the earlier level, we get a representation of size 4. But if you fetch it even at an earlier level, we get a representation of size 2. So this is the advantage of Retrieval, that we can get dense embeddings of various different sizes based on the level from which you choose to fetch these probability distributions. So each level of Retrieval gives us a valid representation. Mostly the advantages with the shorter representations, it means faster inference. And the first graph here shows this. So it shows that as we increase the size of these representations, the latency, the milliseconds per query, increases linearly. But also the second graph here shows that as we decrease the size of the representation, we do suffer a loss in recall at 10 metric that we saw earlier, but not too much. That the accuracy, the recall at 10 remains quite balanced up until close to 128 as the representation size, and then it drops significantly. So with this kind of curves, it also lets you balance efficiency and accuracy, and it lets you choose as to what representation size works best for your application. So the key takeaways here is that retrieval systems are a really important part of QA with LLMs. We introduced our work Retriever, which is a hierarchical retrieval system. It is fast, it is accurate, it is interpretable, it helps you balance accuracy and efficiency. It is easily trainable, and it also generalizes well. And please do visit our paper and do try our work. Thank you so much.